Okay, we're going to start with number 1 on our ideal gas law worksheet. How many moles of oxygen will occupy 2.5 liters at 1.2 atms and 25 degrees Celsius? The first step to any problem that we're doing, any gas law problem, is to assign the variables. So our variables for this problem are P, V, N, R, and T. Okay. We got our variables from our ideal gas law equation. PV equals nRT. Okay, so pressure. Let's go first. Pressure is at 1.2 atms. 0.2 atms. Volume is 2.5 liters. It's asking for how many moles, so we don't know what moles are. And last but not least, we have temperature in the problem, which is 25 degrees Celsius. R is the ideal gas constant. There are 3 different gas constants, and you choose which gas constant to use based on the units of pressure. In this problem, the units for pressure are atms, so we're going to pick our ideal constant number 1 on our sheet, which is 0.0821. And then we have a long unit, and then we have long units for this. Liters times atms over moles times kelvins. The next step is to convert our temperature to kelvins. You do that by adding 273 to whatever the temperature, to whatever Celsius temperature is given in the problem. That, adding those together, will give you 298. Okay, now I'm going to pull my calculator right here so y'all can see what I'm doing. Here we go. Okay, next step, we're going to plug in all of our numbers. So we have 1, I'm going to drop the units just so it's easier to read. 1.2 atms, which I'm not writing, 2.5 liters equals N, which we don't know, so I'm just going to write an N right there. And then we have R times R, 0.0821. And then, last but not least, we're going to add our kelvins, which is 298. Okay, so now we're going to solve for each side, and then we'll get N by itself. So this side, the left side, 1.2 times 2.5 equals 3. And then now we're going to multiply 0.0821 times 298 gives us 24.4658. And we still have this N. We want to get the N by itself, so we're going to have to divide both. These are being multiplied, so we're going to have to divide both sides by 24.4658. And once I'm going to put this into our calculator. There we go. And we have 0.12 moles. I chose 0.12 because if you look back to the number, we have to do significant figures, and you always pick the least number of significant figures in this problem. Pressure, there's 2 significant figures. Volume, there's 2 significant figures. R, for our ideal gas constant, there's 3, and then for our temperature, there's 2. So I picked 2 significant figures. Now we're working on number 2 for our ideal gas law problem. Step 1, let me straighten this really quick. Step 1, assign our variables. P, V, N, R, T. Okay. What volume will 2.0 moles of nitrogen occupy at 720 milliliters of mercury at 20 degrees Celsius? Okay, so the question is looking for volume. So we don't know how much volume we have. We have 2.0 moles. Then we have 20 degrees Celsius. And we have 720 milliliters of mercury. Milliliters of mercury is another unit for pressure. So now we have to go up here, look at which ideal gas law constant we need. Okay, so let's go, nope, this is in ATMs, this is in kPas. Perfect. Milliliters of mercury, or mmHg. So we have 62.4, and then we have 62.4 is our ideal gas constant. Okay, just going to finish writing these units out. And now, step number 2, we have to make sure we add 273 to our temperature so we can get it in kelvins. That's going to equal 293. 20 plus 273 equals 293. Okay. Now, next step, plug in all our variables. 720 V equals 2 times 64 times 293. I'm just going to write, because we know our answer is going to be in liters, so I'm just going to write liters over here. I'm going to make a box for our answer. Okay? First thing I'm going to do is I'm going to multiply this side together. So we have 2 times 62.4 times 293. This side gives me 36,566.4. And then I want to get V alone by itself. So I'm going to divide both sides by 720. Because the 720 is being multiplied by the V, so you do the opposite to get rid of it. Divided by 720. Perfect. And the answer is 50.7866 repeating. Okay? Now we need to figure out how many significant figures we need in this problem. Okay? In this problem, we have 2. In this problem, we have 2, 2, 3, 2. 2, 2, 3, and 1. So we're going to round it to one significant figure. Okay? So it ends up being 50 liters. And that is our final answer. Okay, now we've moved on to number 3 on our ideal gas law. Worksheet. Number 3, how many atmospheres of pressure will be exerted by 0.57 moles of CO2 at room temperature at a temperature of 25 degrees and a volume of 500 liters? Okay, first step, assign variables. Okay, so we have P. It's asking for P. We don't know, but it does tell you that we're looking for it in atmospheres. Our volume is 500 liters. Our temperature is 25 degrees Celsius. And then our moles are 0.57 moles. There we go. And now we need R. It's asking for It's asking for ATMs in the problem, atmospheres. So we're going to look up here. We're going to find the ideal gas constant that has atmospheres in it, which is number 1, 0.0821. Next step, make sure we add that 273 to our temperature, equals 298 kelvins. Next step, we're going to plug in all of our equations to our ideal gas law, which is PV equals nRT. So P, we don't know. V is 500. If y'all remember, I dropped the variables to make the problems more concise and easier to read. And now we have equals N, which is 0.57 moles. And now we have our R, which is 0.0821. And last but not least, we have our temperature, which is 98 degrees kelvins. Okay? First step, I'm going to multiply this. We want to get P by itself. But first step, I'm going to multiply the right side of the equation together so I have one nice number. So let's get that done. 0.57, sorry, that's a 7, times 0.0821 times 298. Bam, that is 13.945506. And I want to get the P that's on the left by itself. So I'm going to divide this 13.94556 by 500, because in order to get, we're multiplying by 500 on this side, so we have to divide by 500 on both sides to get our answer. And the answer is let's see, how many significant figures are we looking at? One significant figure. If we're looking here at volume, that's just one, so it's 0.03, because we're going to round the 2. We're going to round the 2, and since the 7 is above 5, we're going to round it to 3. Okay? So that is the pressure in ATMs, 0.03. It's very, very light pressure. Okay?